Welcome students to Unit 4. Unit 4 is broken into two parts, ionic bonds and covalent bonds. So we will first tackle ionic bonds today, but before we do, we will look at metallic bonds. In the last unit, we looked at atomic structure, the atoms, protons, neutrons, and electrons. However, most of the universe is not atomic. It's mostly not just atoms. Those atoms are held together in larger structures. Some metals appear elementally, where you can have a block of gold that's just gold atoms, but those atoms are held together by some sort of an attraction. So elemental metals are anything on the left side of the periodic table. If you draw a diagonal line from boron, because chemistry is boring, everything to the left of that line is a metal. And metals have all the properties you think of when you think of a metal. That they are shiny, that they have a luster to them. You can bend a metal, that's very malleable. Metals are ductile, meaning if you heat up a metal, you can pull it apart, and it pulls apart kind of like silly putty. When you pull silly putty apart, it gets those gooey strings between them. That's how metals are formed into wires. The ability to do this is known as ductility. Metals are often solids at room temperature, with one exception. Mercury is a liquid at room temperature, and metals are excellent conductors of energy, either heat or electricity. Now, the reason metals have these properties deals with what holds metals together, the attraction between the atoms of a metal, metallic bonds. Metals have excess electrons, so metals will often lose those electrons to form different bonds, which we will focus on later in this unit. However, metals actually have so many extra electrons that they actually give them up, forming metal cations. Metals exist mostly in this cation state, where their extra electrons they share between them. So metals are often described as cations in a sea of delocalized electrons. These non-directional attractions between the metals and these free-floating electrons is what gives metals their properties. So metals are excellent conductors of heat because all heat is movement. These metals are set up in a lattice-like structure. Lattice like the thing that's under your deck. That lattice structure under your deck, if you shake one part of it, the rest of it shakes as well. So metals conduct heat very well because of this strong attraction that holds them in a lattice-like shape. Metals are also excellent conductors of electricity because since they have these non-directional attractions for electrons, if I drop an extra electron in, because that's all electricity is, the other electrons shift and move, and eventually an electron comes out the other side. And it doesn't take a lot to do this. It's like putting a drop in a cup that's already full. A drop immediately falls out. So metals are excellent conductors of both electricity and heat. It is very rare to come across a pure metal, a pure element. As we talked about in previous units, there's very few objects that are solid gold. That's because these elements have distinct chemical properties and often will oxidize or react with the oxygen in the air to rust. So we usually see metals in the form of alloys. Alloys are a mixture of two or more metals. Now there are two types of alloys, a substitution alloy and an interstitial alloy. A substitution alloy happens between metals with a similar radius. So metals in the same period tend to form substitution alloys. For example, copper and zinc come together to form the alloy brass. Copper and zinc have approximately the same radius, so brass is formed when you take a bar of copper and either through chemical or physical means cause the atoms to move slightly apart, and you drop zinc atoms into them, thus substituting one cation for another. Since they're a similar radius, the atoms simply shift and replace one another. Interstitial alloys are formed between atoms of very different radii. So for example, iron and carbon come together to form steel. Carbon is a much smaller atom than iron, and therefore it actually can fit in the spaces between the iron atoms, and thus mixing them together causes the carbon to fall into those spaces. Alloys give metals slightly different properties. So for example, gold is a very, very malleable metal. It's very bendy. That's that old in those old-time pirate movies, when you see the pirate bite the gold, they used to bite gold to prove that it was pure gold. If your teeth left an indent in the gold, that was a pure gold coin. They don't make gold coins that way anymore. They mix in other elements to give gold a little bit more zest. In lab, this class, we will make a substitution alloy by making brass in our golden penny lab. If you are not in class, you unfortunately will miss out on making a golden penny. However, if you are here, you will have made your golden penny. I will see you next time when we get to ionic bonds.